Hello everyone and welcome back. Now, are you having as much fun as I'm having learning about autoencoders? Because I can tell you, I'm having a great time. And I am very excited to talk to you today about more autoencoders and another one of my favorite things of all time in dynamical systems, the Koopman operator. Okay, so the goal here today is to unite the Koopman theory that we learned about way back when we talked about extended dynamic mode decomposition and kernel methods with the very sort of new, or at least new to this lecture series, idea of autoencoders. And the goal will be to sort of replace that original EDMD idea of having a dictionary with the idea of letting the neural network learn the dictionary that is best suited to the data that's provided to it. So before I begin with the neural network aspect of this, let's start with a little bit of a refresher. Let's remind ourselves, maybe I have a mapping, let's just say from RD back into RG, so it's a d-dimensional function, and let's say that this thing defines a dynamical system, right? So we're going to sort of step ourselves forward in time according to this thing. Now what I want you to remember is the Koopman operator, right? So Koopman acts on what we call observable functions. So remember, I take some function, I'll call it psi. It's a function from RD into potentially the complex numbers or just any sort of scalar field for those that are feeling very mathy behind us or behind the screen today. The real numbers, the complex numbers, it doesn't really matter. But what it does is the Koopman operator evolves the system. So Koopman of psi, remember Koopman acts on these observable functions, which I can remind you, observable. Koopman acts on these things through function composition. And remember, we saw that this action really is pushing forward the dynamics inside of these things. And in particular, the eigenfunctions were the things that we really cared about. So eigenfunctions. And eigenfunctions satisfy the following relationship. Well, it's k phi or k psi is equal to mu psi, but that really is this relationship right here. Right? That is what we care about. And in particular, if you do this at a specific data point, right, this is going to tell you that psi of f of xn, which is xn plus 1, is equal to mu of psi of xn, right? So it says that if I want to move forward in time inside of the observable, I just need to multiply by the eigenvalue. That defines a linear relationship. And in particular, if I have an orbit, let's call it x0, x1, x2, x3, and so on, that are all mapped forward into each other by the function f, right? So an orbit of a dynamical system, right? Then what I could say is that if I look at psi dynamics inside of this thing, I could say that, well, really, psi of x1 is equal to mu psi of x0. And I could say that psi of x2 is equal to mu squared of psi of x0 through induction. And in general, psi of xn is equal to mu to the n of psi of x0. So this tells me that if I just put my dynamics or my data in the right coordinate frame, right? So instead what I could do is wrap it in the psi variable. Well, in this case, if I say Zn is equal to psi n, then this relationship I have over here is that Zn plus 1 is equal to mu Zn. That is a completely linear dynamical system. It is global as well, right? So it is global in the sense that psi acts on all of the space. It does not matter where the data comes from. This is not Hartman-Grobman. This is not local linearization. This is global linearization of the dynamical system. Now, of course, your clearly losing information, right? This was a d-dimensional system. Hopefully d, d could be 100, it could be 1,000,000, it could be 3, it could be 2, whatever. This is really just a one-dimensional output, and it might not have that much significance. But what you could do instead is look at a whole bunch of eigenfunctions. Okay, so let's imagine I've got R eigenfunctions. So let's imagine now I have psi 1 all the way up to psi r. That should be an R. I hope you can tell that's an R. Koopman eigenfunctions. And let's assume they have eigenvalues. So with eigenvalues, I'm going to say mu1 all the way up to mu r. Remember, these things could be complex valued. That's totally fine with me. But if I do this for every single, so if I repeat this whole task for every single Koopman eigenfunction here, what I'm actually going to get is a great big linear dynamical system, Z1, Z2, all the way down to ZR. And if I want to push this thing forward in time, okay, if I want to go forward in time, what do? I multiply by not only a matrix, a diagonal matrix, my friends. Life doesn't get much better than that. Honestly, as a mathematician, I can say that with perfect honesty and clarity. Look at that. Sorry, this is MR down here, or mu r. And then Z1, Z2, ZR at time n. That is incredible, okay? Now, the only drawback here is that Z could be complex valued. So what we would like to do is we would like to turn this into a real valued system. And what we're going to have to do, because these are complex valued, we're going to have to double the dimension here, right? Because you can always think of C as being sort of isometrically isomorphic to R2. And so in this case, what I'm going to do is I'm going to say let Zj, right? So each one of these little components inside of this thing, let me make sure I get this right. This is going to be y2j minus 1 plus, let's see, where did this go? Plus I y2j, right? So I'm just doubling the dimension here. I'm opening things up. And let's let each corresponding eigenvalue be alpha j plus I beta j. And so now, if you do this, you get a 2R dimensional system. Okay, so this becomes now y1, y2, and then I'm going to go to y, let's say 2R minus 1, y2R, and then n plus 1. Now, each one of these blocks, right, or each one of these diagonal components turns into a block. So I get alpha 1, beta 1, minus beta 1, alpha 1, right? So if you're familiar with, if you've taken algebra classes or maybe some of your calculus classes, they've sort of done this little correspondence between complex eigenvalues for diagonalization and these sort of block terms. Sometimes we call these Jacobi or block diagonal matrices that are coming from the Jordan normal form, sorry. And then here I have alpha r, beta r, minus beta r, alpha r, and then I've got 0, 0, 0, 0, right? So this is just a Jordan form for this thing written in real coordinates, y1, y2, y2r minus 1, y2r, and this is at time n plus 1. So why is this important, right? What was the point of you going through all of this, Jason? Well, take a look at this. If I can find these functions, I have a conjugacy, or at least I have a transformation to a linear system. So if I call this thing, I'm going to call it capital psi of x, which is just going to be, it's going to be a huge coordinate vector. So it's going to be the real part of psi 1, the imaginary part of psi 1, and then so on and so forth. The real part of psi r, the imaginary part of psi r. Transpose. This thing is going to map from RD into r to the 2r. Okay? So it takes in an input in original RD space, and it maps out to the double R space, so the number of eigenvalues or eigenfunctions you're using, and then doubling it up because of the real and the imaginary parts here. And if I call this linear mapping, let's put a different color on it. If I call this thing g of y, well, what have I done? Then what do I have? If I take psi and compose it with f, right? So that's all of these things at xn plus 1. This is the same as g composed with psi, right? It is the same as transforming to these coordinates and pushing forward in time by 1 time unit. This right here is basically the conjugacy relationship. Now there is a major caveat here. This can never actually be a conjugacy if d and 2r are not the same number, right? Because we know space, these real coordinate frames of different dimensions can never be homeomorphic if they have a different dimension. But that's good enough. That's good enough for me to sort of build a neural network around. You can think about phi as being your encoder. It's not a perfect topological conjugacy, but it doesn't have to be. It's a transformation. And it makes my life simpler. Look at this is a linear system, and each output of the encoder describes an eigenfunction of the neural network. Now the question is, how do you build the decoder? Well, it turns out that the decoder here can be done very, very simply, because the decoder is going to help you select the right eigenfunctions to choose here. Because again, if you think about putting this into a neural network, trying to build a loss here, we know that the Koopman operator has a whole lot of eigenfunctions. Remember I showed you that you can multiply eigenfunctions, you can get more eigenfunctions out of that, right? Horrible property. That means there's so many eigenfunctions, it's hard to choose which ones you want to think about. And if you don't have a decoder enforcing anything here, you just have a transformation to a linear coordinate frame, and that linear coordinate frame might actually sort of hold nothing of interest for you, in the sense that the eigenfunctions that are being used are not helpful. Here is how you build the decoder in. Remember, if you go back to that EDMD lecture that we had, the purpose of finding sequences of eigenfunctions was to linearize the original mapping. And what we did with that is we wanted what we called the state observable x to be written in the span of these eigenfunctions. So here's what I want to happen. I'm going to go from j equal to 1 to capital R, and I'm going to look for a number aj, so that the real part of psi j of x plus a number bj times the imaginary part of psi j of x. When I put all of these things together, the state observable is going to be in their span. The decoder here, all right, so again, if maybe you're having trouble seeing this, and I'll show you an example in a second. This is my decoder. It's linear. The only things to tune are A's and B's here. This is super cool, right? I think that this is amazing because it's a way of finding Koopman eigenfunctions as part of an autoencoder relationship where the decoder is completely linear. The encoder, the outputs are the outputs of the Koopman eigenfunctions, and the result is a completely linear characterization of a nonlinear system, right? This is amazing to me. I think that this is one of the coolest things that's ever been done with autoencoder neural networks, especially as it relates to dynamical systems. Let's take a look at an example that we've actually already seen before. We're going to use the same nonlinear system that we used for EDMD, so that's extended dynamic mode decomposition. So here it is on the board. It's a two-dimensional mapping from R2 to R2. Remember, we have these two parameters. We call them lambda1 and lambda2. It's linear in the first component. It's nonlinear in the second component. And the reason we wanted to use this mapping is because it's one of very few dynamical systems where the at least important Koopman eigenfunctions are known. Right, so what I'm doing is I'm writing down these three Koopman eigenfunctions. Remember from the original video where we learned EDMD, we went through all of the sort of analytical steps of showing how this linearizes the system as well. Of course, there are more Koopman eigenfunctions, and they just come from sort of multiplying these eigenfunctions together. So sometimes we call these like the base or the fundamental Koopman eigenfunctions. But the basic idea here is pretty similar to what we've seen previously, okay? So here I'm going to choose 5,000 data points from the grid -2 to 2, and I'm going to do that as a square because I have two components, x1 and x2. And then what I'm going to do is I'm going to learn where they go underneath the map, the forward iterates, and this is going to be for the loss function. And then I'm going to set up my conjugacy neural network. Again, you can see like I'm really sort of like copying and pasting the basics of these things and then just adapting them to the different flavors and the different applications that we're using. Now, this application of global linearization is slightly more involved. It's not a true topological conjugacy, even though it's inspired by a topological conjugacy. And that means that this is really where you'll see the most differences in the neural network, at least how it's set up. So in particular, I have three variables. I've called them A1 and A2 and A3. These are the Koopman eigenvalues that need to be discovered as we go along. They are trainable parameters of the neural network. Here I've initiated their values at the true values just so that I can speed up the computation. But of course, you would want to randomize these things and let the neural network learn it. Another piece of this is that I am trying to learn a mapping from a two-dimensional system to a three-dimensional system. So R is equal to 3 in this case. I'm just going to consider real valued. At the end of this script or this notebook, I also consider complex valued. So a 6-dimensional system, it performs almost exactly the same. So I'm just showing you the real valued results to start with. But of course, doing this in practice, you need to choose the value of R. That's a hyperparameter, right? And so typically you have to optimize over this. Choosing larger R is better. And I have some examples in the book that I call upon where people applied this sort of neural network architecture to more complex systems like the chaotic Kuramoto-Shibashinsky, where R is like 128 or something like that, right? So in my case, I know the answer, so I can set it up. But of course, the reason we're doing this is to gauge performance so that you, the watcher, can do this and you can take it and you can apply it to your favorite dynamical system or your favorite application, your favorite data set. And again, let me know in the comments. I want to hear about how people are using these things. So here we are, we're defining the encoder and the decoder. Now, in particular, the main difference here is that the decoder is a single linear layer. Remember, that's the AJ, BJ terms that are coming out of this thing. But for the most part, the losses are exactly the same. L1, L2, L3, you're just sort of putting this all together. Now, you don't have the usual sort of inverse relationship between the encoder and the decoder, but because of the way we've defined these things, you have the decoder functioning as a left inverse of the encoder, not a right inverse, right? Because if it was a right inverse, that would tell us that RD and RR are homeomorphic. So here running this, I'm going to use a width of 200 I'm going to say that my encoder has a depth of 6, so quite a large neural network. It's getting close to what you would refer to as deep. The dimension of x variables that are going in is 2. The dimension of the y variables that are coming out, in this case, because we're just using the real components, is 3. For the second half of this notebook, it's going to be 6, right, because you use real and imaginary. And here I did a little bit of training. This one is very, very bad. It should have been trained for a longer time. It's just that I didn't want to wait. But I saved some results and I presented them here for you. Here's what you can see. Here's the discovered Koopman eigenvalues. So 2.24, 0.499, 1.499. The exact values should be 1.5, 0.5, and 2.25. These are very, very accurate. I did a lot of training to get these results. And for the linear layer, here you can just spit it out because the linear layer is really just a matrix. It's real and imaginary. It is, each piece of this is reconstructing the x1 and x2 variables. So going down the columns here is telling you how much of each one of these eigenfunctions or these outputs of the encoder function is being weighted. Now, I wouldn't pay too much attention to the exact values because there's always a scaling. So, if this 1.7 should actually be a 1, then there is a 1 over 1.7 hidden somewhere in the inside of the encoder, okay? So there's this sort of degenerate relationship where really you're sort of just looking at the active values, right? So you can see 10 to the minus 3, 10 to the minus 4, 10 to the minus 2. Those things should be sort of numerically 0, and we're really sort of looking at these active values here. In particular, we can approximate the eigenfunctions here. Now this is showing from 2 different trials. This is the real output of the encoder function. Here, this should really be x1, right? There's no x2 dependence. That was the first Koopman eigenfunction. This one should be x1 minus x2 squared. There might be some numbers in there as well. And this one is just x1 squared. And this is almost a perfect alignment with what we saw the exact answer should be. So again, go back, maybe get your pencil and paper out, find these Koopman eigenfunctions, and then compare at least the shape and the characteristics of these things to what we're seeing this output from the neural network is. Now, of course, this is a simple example, but it's proof of concept. And this is a beautiful idea that has been applied to much more complex systems. I mentioned the Kuramoto-Shibashinsky. There's applications to burgers. I've seen people do this on shear flow models. It is an excellent way of analyzing a system using the Koopman framework, but allowing yourself to get away from the dictionary that EDMD requires. In this case, the encoder is finding the dictionary for you. That is the real innovation of this. It is beautiful. It's sort of dictionary free. Okay, when we come back in the next video, we're going to look at action angle coordinates, a specific example of these Koopman autoencoder neural networks where we know the exact value of R that we need to be targeting. So I'll see you all in the next video, everybody.